Swayam Prabha. Digital India. Educated India.
Right, I think we can get started. Good morning. Thanks for being here, despite it being Saturday. Apologies for making you come. Anyway, so let's quickly recap what we have done so far. So, kind of recall, we are talking about developing an effective formalism that we treat light as an electromagnetic wave, matter as composed of discrete quantum states. And we want to develop an effective formalism which can capture the essence of spectroscopy, both linear as well as nonlinear. And an essential ingredient in that is that the Hamiltonian that we are dealing with has two components to it. One is a time-dependent part, and a time-dependent part exclusively coming because of the interaction with the interaction of the light and matter. We have not disclosed. I mean, I kind of disclosed already what is the form of that interaction potential. Right, it's minus mu dot E. But hopefully in this class we will actually derive and see where this magic expression comes from. But we have also seen the generics of general formalism of how to solve time-dependent Schrodinger equation for a time-dependent Hamiltonian, because we do have a time-dependent Hamiltonian. And part of that was the exercise that we went through regarding the Dyson time ordering, which is an important ingredient, whatever we do. And we also kind of briefly introduce ourselves to the concept of density metrics and von Neumann equation of motion, which tells you the evolution of your density matrix, which is the critical part. And we have also seen how density matrix helps you to kind of not care about the wave function, the amplitude of the wave function itself, because what we want to worry are two important things: populations and coherences. Population, coherence. Population is dealing with the diagonal component of your density matrix, basically telling you probability of occupation of a given quantum state, and off diagonal elements talking about coherence, or what is coherent superposition states, possibly driven by an external perturbation, in this case electromagnetic wave. Okay, so that's the kind of concept. Now in this class, so this is kind of a broader perspective of essential quantum mechanics required for this course. In this class, we will go a bit deeper into light-matter interaction particularly. So we have not really spoken about light-matter interaction so far explicitly. It's kind of there in essence, but we have not explicitly developed light-matter interaction. In this class, we are going to specifically understand light-matter interaction and how to deal. So for this class, I will not be, the next 1 hour, 2 hours, whatever it might take, I will not be using the density matrix formalism. Okay. And you might ask me, come on man, you just told us that density matrix is an effective way, and why do you want to go back and deal with all your wave functions and amplitudes? The reason is I want to start developing simpler versions of it to get you a physical intuition of what the process is. In the next class, we will going to start attacking the density matrix and develop what is known as optical blocking functions. That's for the next class. So this class, light matter interaction, again, we are not going to use density matrix. We're going to directly work on the amplitudes of your wave function or time evolution of the amplitude of the wave function, and understand what are the signatures of this light matter interaction, what can light matter interaction pull out, what property of the material will it pull out. Okay. All right, so we'll start with the first topic. The first topic is going to be resonant driving of a two-level system. Simple. So what we are going to consider is some initial state, some final state, and let's say we are driving this two-level system with an oscillating potential. Okay, let's say your V of t is V cos omega t. It's some potential which is driving it. I didn't say anything about light matter interaction so far. It's some time dependent potential driving. It's a resonant driving. So happens it's not that different. The potential that I have just written here is not that different from what is expected of an electromagnetic wave. So kind of has roots in light matter interaction, although I didn't explicitly spell it out. Now, what are we asking? We are asking the question, by driving the system with such a potential, and assuming, of course, the system starts at the initial state I, what is the probability of finding the state in F after a given time t? Right? That's the question. That's a very simple and the most obvious question to ask. So I'm driving the system with a potential. My system is in the initial state, the ground state, to begin with. After a certain time t, what is the probability that I will find my system in the excited state? Right? So to do that, of course, we know how to kind of deal with such a problem. We need to write out the equation of motion for the amplitudes of the wave function. Right? So if I write that out, remember B's, right? There are not C's. B's are in the interaction picture, but I'm not going to revise those parts. Only two-level system, which is easier. Okay, so this is not that different from what we have already seen in the last class. Write out the equation of motion for the amplitudes. Basically, it's kind of the interaction picture. Now, if I write down V, which is V cos omega t, in its complex form, right, I can kind of expand this out a bit more. I mean, it's nice to have this equation for a generic GK, but we know we have only two states, I and F. So I should be able to explicitly write out the equations for BF and BI, right? Because that's what we are interested in. Let's do that. So for BF, it will be H cross D over dt F half BI BFI power I minus d plus e to the power I plus omega d plus plus half BF BFF I omega t plus e to the power minus I omega t. Similarly, I can write it a similar looking equation for Bi. Now, can anybody tell me what will be value of VFF? So V is your interaction, right? Potential is coming in. In this case, it's a 2 by 2 matrix. So the diagonal of this interaction potential will be 0. So the interaction potential will only have the off diagonal terms because it makes sense. Right? There is no point of interaction onto itself. That's kind of meaningless. Okay, so this term will go away. So you're left with only other term. But even if we look at other term, there are two different components to it. One which is oscillating at this difference, one oscillating at pretty large frequency. Okay, pretty large frequency. So when I'm driving the system close to the resonance, let's say my omega, which is the system at which I'm driving the system, omega, let's say it's close to omega fi. Then you'll see the second term here is oscillating at relatively large frequency. And basically, you can kind of say that the oscillation is so rapid with respect to the oscillation of your perturbing interaction potential that you may as well ignore it. As I kind of already alluded to you in the last class, it's kind of the basis of what we call as rotating wave approximation. It's going so fast that you just don't care. You ride the wave on top of it. Okay, so but the important thing is that this approximation is going to be valid only if we are driving the system at a frequency which is closer to its frequency, omega fi equal to. So we are operating close to the resonance condition. Okay, that's one of the important prerequisites for rotating wave approximation. Okay, so far so good. Okay, if I do this, then I can simplify my equation. My equation now will become d f minus I cross I b I over I omega fi minus omega t. That is one equation. The second equation, ed bi will be minus I h cross bf if, not the difference, e power minus I omega fi minus omega t. You can also see from this equation that the coefficients are basically oscillating at the same frequency, but phase shifted with respect to one another. How do we know that? Look at the frequency of oscillation. They're identical, but there is a phase shifting. Kind of makes sense, right? Or convince yourself that it makes sense. Okay, so we can now sort of combine these things. For example, you can take the top equation and do a second differentiate it again with respect to time and combine it with the second equation. It's a bit of math. I'm not going to do that. I'm going to write down a final looking equation which basically combines both these equations. Basically, it's a second order equation which will be d square f square minus I omega fi minus omega d df for dt plus v I magnitude square over square f will be 0. Okay, good. So let's look at this equation with more What do you think this equation looks like? Does it remind you of anything that you already know? Simple?
Damn simple.
It's a damn simple harmonic oscillator, right? And you know how to solve this. So if I have a damped oscillator which looks like this, then you know x will be e power minus b over a t a cos mu t sine mu t, where mu is 1 over a square. Principle, we should be able to figure out this. Remember, at the end of the day, for if I'm doing an experiment or I'm actually interested in something which is physically meaningful, then I'm not interested in BF. What am I interested in? Sorry? No, CF is kind of in a different picture, but what is BF? BF is the amplitude of my wave function, right? What you are interested is the square of that amplitude. That's what you're going to measure. So what we are interested finally is BF, which is the probability of finding my state in F at a given time t, which will be simply this. Make sense? Now, again, it's a bit more mathematically cumbersome. My notes, I have kind of tried to do that. If you are interested, you can kind of go over this. I'm going to write the final looking equation. So if I make appropriate substitutions in this solution of damped harmonic oscillator and calculate the square, I'm going to write out the final equation. My PF of t is going to look t sigma r 1 over r square square. Okay, so it's going to oscillate at a certain frequency, right? It's going to oscillate at a certain frequency, sigma r, which, if you can recall from elsewhere, this is referred to as the Rabi frequency. So basically, the probability amplitude, of course, PF is this, my PI is equal to 1 minus PF. So in this simple picture, my probability is going to oscillate between I and F at the frequency given by the Rabi frequency, which of course depends on the strength of the interaction potential. Okay. Does this again, the fact that the probability is oscillating between these two, does this remind you of something else which we already discussed? Current superposition. So the idea is when I'm coming with my external interaction field V, which is oscillating, it's cosine of omega t, which is kind of similar to what you expect in an electromagnetic field. What you are generating is a coherence. Okay, we're going to show this in a more elegant way using density matrix later on, but that's something for later. The other thing is that if I just look at the amplitude of this oscillation, you know what this function looks like. This is something that you have you come across anytime? Come again? It's a Lorentzian function. Very good. So if I just plot that amplitude, let's call it P of amplitude. It's going to look, it's more Gaussian, I'm sorry, or skewed Gaussian, but let's assume it's Lorentzian. Around omega fi, the width, the Lorentzian, is given by 2 fi over h bar. Okay, so it's kind of what we went through overall is what happens if I start driving the system. When I start driving the system, you will see that the probability of finding the state is going to oscillate at the frequency of the Rabi frequency, meaning that I'm generating coherence because of interaction with a potential, number one. Number two is that probability amplitude is going to taper off as you detune or go away from resonance. Also makes sense. It's kind of as what you expect from even for a classical oscillator. Nothing spectacular there, but it's kind of good to see that. And the full width half maximum of that Lorentzian function is of course related to the strength of the interaction potential. Okay. Now something this does not explicitly consider is any kind of damping coming from the system bath interaction. Okay. So there is nothing which is telling, oh, at some point they should damp off. This is going to oscillate forever, which is of course physically not meaningful, which in a realistic system, you are inevitably going to have system bar interaction, which is something that we will treat in this class. Okay, but for now, so far so good. So far so good. Okay, now we need to find now a kind of form for our VFI, which is going to appear everywhere, right? So what is this VFI? If I have an electromagnetic field, I kind of alluded that this VFI is going to look like cosine. Is it really true? Not really. What will be the amplitude? So we have to figure this out. And for that, we are going to take a slight detour into classical electrodynamics. Forget quantum for now. Let's go classical. Then we'll come back. Any questions so far? Okay, good. So the question that we are asking, what is the relevant VFI for electromagnetic waves? So for that, we need to first figure out classical Hamiltonian for a radiation field interacting with a charged particle. Kind of makes sense. We are kind of dealing with such thing. Of course, at some point, we should move away from the classical Hamiltonian, actually quantum Hamiltonian, quantized Hamiltonian, but that will come back later. But let's write down the classical Hamiltonian. I'm sure you have already done it in some classical mechanics course, but let's write this out. So if I take a charged particle, and I know force, the Lorentz force on the particle. So remember, we are trying to look at classical Hamiltonian for a radiation field interacting with a charged particle. So have a radiation field, electromagnetic field, and the force will be Q E plus V cross B. You all know this. And I can write down this force in terms of the potential energy of the system. X. So again, working with electric and magnetic fields is cumbersome. There is more elegant approach. Instead of using fields, what do we use in classical electrodynamics? We don't want vectors or try to reduce vectors. We use what? Potentials. We use electrostatic potential and the vector potential. So we'll replace E and B with vector potential and scalar potential. That way we don't need to bookkeep 6 terms, we just need to bookkeep 4 terms, 4 parameters. Okay, So if I do that, then my potential energy of my associated with electromagnetic field, no, is given by this. We have to write out the classical Hamiltonian from this. So I'm going to write out the Lagrangian of the particle, Lagrangian. What is Lagrangian?
T minus Q is
Okay, yeah, you already told me the final one. So T minus V, let's write, start with that. So that will be half mv square plus Q V dot A minus Q phi. V here is related to that potential energy. And we know momentum term V d L d V mv is Q A, which means V is 1 over m V minus Q A. Why do I write the momentum? Because now we know classical Hamiltonian. I can use both this momentum and the Lagrangian. Write my Hamiltonian to be P dot V minus L. If you make these substitutions, which I'll leave it to you, it's not possible. You will see this will be equal to 1 over 2m V minus Q A square plus Q phi. That's your classical Hamiltonian of the radiation field interacting with a charged particle. Now I'm going to say, I'm going to work in Coulomb gauge. Because I like it to be simple, and phi will be 0, which means H Hamiltonian. Simplify even further. A slight detour statement here, or a disclaimer here. Using Coulomb gauge for electromagnetic fields is a bit questionable. One might argue that Coulomb gauge is not appropriate for electromagnetic fields. We will not get into the discussion at this point in time. For the sake of our weak coupling limit spectroscopy, Coulomb gauge is okay. However, once you go into strong coupling, this may be questioned. One might argue we may have to work in the velocity gauge. But that's disclaimer there. We are making an assumption explicitly. So whenever you see mu dot E, there is an implicit assumption there that we are working in the Coulomb gauge. That's why I'm writing this out explicitly. So that need not be valid. Okay, cool. So this is the radiation field, but of course, if I have in a realistic system, what I have is a single particle in some bound potential. It's not a free particle. So in the absence of the field, you're fine with this. So for right or a single particle bound potential, let's say V naught, which is not time varying, it's a bound potential. In the absence of field, my H naught will be 1 over 2 m E square plus V naught R. In the presence of field, now let's turn on the field. In the presence of field, you need to add the other term. So if you add the other term, your total Hamiltonian will become H naught minus Q over 2m. It's an intermediate step here which I'm skipping. My notes will have it. Okay. So what I did is I just added, go back. So I took this guy here, expanded that out, added to this potential here, and simplified it further, and I get this. Now we are going to make some assumptions here. We're going to make the assumption where the a squared term is negligible and you'll ignore it. When do you think that will be a valid thing to do? When do you think I can ignore this a squared term here completely? Let's say let's go to the weak fields, weak perturbative fields. So this sign, because a value of vector potential is small, a square will be much smaller. So implicitly I'm saying I'm going to work under weak sort of perturbative field. Then life is simple, kind of see my v of t now that I'm interacting field is some q over 2m v dot a plus a dot b. So this is still classical. We have not figured out final classical. I dropped also the negative sign because it's a charge. Okay, fair enough. Fair enough. Now we have to make the jump from classical world to quantum. Which part of this potential we need to translate into the quantum world? And there are only two there, P and A. So what will you make? Which one of them will you make quantum? Momentum. Because we are in the semi-classical limit. So A is still classical. A vector field, vector potential is classical. So I need to now replace my P with what? With an operator, right? So now we are going to make quantum mechanical Hamiltonian. So for doing that, we're going to say my P is minus I H cross the L operator. So now my V of t becomes I H cross over 2m q divergence of A plus A dot L. Can I make any more simplification here? What is the gauge I have chosen? Coulomb gauge. So what is the property of my vector potential in the Coulomb gauge? Divergence of my vector potential is 0 in Coulomb gauge. So this is 0 because of Coulomb gauge. Life really simplifies with Coulomb gauge. of t minus q dot m a dot p. Yeah, that should be fun. Basically, I'm making this, substituting back my del operator with my p momentum operator. That's your potential. Okay, a dot p. So that's something that you can quickly remember. So there's still no dipole approximation of any kind. My interaction potential, basically in the quantum domain, for a classical electromagnetic field interacting with some quantized matter, will be minus q dot to m a dot p. A dot p is something that you can stick, kind of keep in your mind. P is the momentum operator. Okay, good. This is for single particles. For multiple particles, we can generalize it. So for general multiple particles, my v of t minus j qj j j t dot j. Now I can write out my a in terms of, I'm going to write out my, expand my a in terms of some plane waves. If I do that, plane wave approximation, some amplitude for my vector potential in unit vector associated with it, Vj e to the power I k dot r j minus omega t. You also have conjugate star in the unit vector associated with it, Vj dagger power minus I k dot rj minus omega t. Okay. Under most circumstances, I'm going to say we can neglect the wave vector dependence, kind of forget the k dot r term. Is it really valid? Do you think it's valid if I just forget k dot r? We can neglect, exactly. And also, you can also think that you're looking at an ensemble average. If I have an ensemble average, it doesn't matter, it kind of averages out, right? So you can kind of, there are some specific cases where you cannot neglect this, but again, in the decoupling regime of dilute chromophores, for example, we can as well neglect it. In some cases, you cannot neglect. But for now, we're going to say we neglect the wave vector dependence. So if I neglect that, and also considering that my A naught, the amplitude of vector potential, is of course related to my electric field amplitude, assuming that you remember your electrodynamics. So then you can write out my V of t minus IQ E naught over 2m omega unit vector operator. Remember, this is a unit vector of the vector potential. This is an operator, momentum operator, e to power minus I omega t minus dot p to power plus I omega t. Now simplify this, minus q e naught over m omega e dot p times sine omega t. And given that my electric field is E naught sine omega t, or at least we assume a sinusoidal electromagnetic field. I can now reduce this even further as simply E dot P. Again, for a collection of particles, you just need to write out a summation. I'm not going to explain. Let's write it down. For collection particles, V of t minus j for j. Okay, cool. I'm not simplified yet. It looks still cumbersome, but this is my V of t. Okay. But if you recall from the previous section, the relevant thing are the matrix elements of my V, which goes into my interaction potential, VFI, right? So what I need to calculate is VFI, which will be F V of t I, which again for a simple case, not multi-particle, not for omega. Okay, we just making things go around. It's not substantial, but important thing again, as I said, we are in the weak field approximation. Weak field approximation means that I can use perturbation theory to solve this out. So in the first order perturbation theory, I can estimate the matrix elements using the unperturbed wave functions, which are related to my H naught, right? So just to evaluate, so especially here, the most critical thing is evaluating this matrix element. We use the fact that commutator bracket of RH naught will be IH cross B over M. As we know. So accordingly, now my F B I will be M over IH cross F R H naught H naught R I. Expanding this out, M over H cross F R I E I, the eigenvalue, minus F R I. I can kind of pull this out and say I am omega Fi. Basically, I do EF minus EI, kind of pull it out. F R I. Basically, now I am able to rewrite this matrix element associated with my momentum operator with a position operator. You will see why this is going to be useful. Let's go back into our VFI here. So you will see now I can write my VFI Vfi to be IQ E naught omega Fi over omega F. Now position vector R I kind of replace that. Always working with multiple charged particles, kind of generalizing this to many charged particles. Go to the next slide. Okay, for multiple charged particles, my Pfi will be minus I naught omega Fi or omega F E dot sum over J's Q J R J, the position operator. Now we define dipole operator mu sum over J Q J R J. If I do that, my V Fi minus I E naught omega Fi over omega F E dot mu, right? Which is simply, if you look at this, simply my matrix element of my dipole moment operator. So this is minus I E naught omega Fi omega mu Fi. Thus, what you can kind of see from here is my V of t is simply minus mu dot mu dot E because dot product is embedded here. We kind of move away from this A dot P explicitly. Is basically we're able to replace my momentum operator with the position operator, and then from there the dipole operator based on that, and we're able to work dipole approximation of the interaction potential is simply the dot product electric field associated with the electromagnetic field. Okay. Do your position operator multiplied by the charge of the particle. So out is we start out with resonance driving. We're going to generate a coherence, and that with if it is happens to be driven by electromagnetic field. Okay. Now the next step is spatial part through system path interaction. A short break, 15-minute break. Okay. Is it okay if we take a little? Yeah. So
Let's take a break now.
let's take a break. Back and briefly go over the next step is okay. Now, how am I going to introduce path? How am I going to define? And secondly, what are the implications of this path that I have figured out? Is there an implication? So figure once we finish that, then we will kind of brief intro to then what's coming in the next class.